In each of 43 through 49, a sequence is defined recursively. Part A, use iteration to guess an explicit formula for the sequence, and Part B, use strong mathematical induction to verify that the formula of Part A is correct. 45 says v sub k equals v sub the floor of k over 2 plus v sub the floor of k plus 1 over 2 plus 2 for each integer k greater than or equal to 2, and v sub 1 equals 1. Let's start by using iteration with part A. The way we do iteration is we evaluate the next few terms in terms of v sub 1. So v sub 2, according to this recursive definition, which we can apply since the index value is greater than or equal to 2, this is equal to v sub the floor of 2 over 2 plus v sub the floor of 2 plus 1 plus v sub the floor of 2 plus 1 over 2 plus 2. This can be simplified to v sub, now 2 over 2 is just 1, and if you round the integer 1 down, you still get 1. And then 2 plus 1 over 2 is 1.5, and if you round that down, we get 1. And if you round that down, we get v sub 1, and then we have plus 2, which simplifies to 2v sub 1 plus 2. Now let's evaluate v sub 3. According to the recursive definition, this is v sub the floor of 3 over 2 plus v sub the floor of 3 plus 1 over 2 plus 2. 3 over 2 is 1.5, and 1.5 rounded down is 1. And then 3 plus 1 over 2 is 2. And if you round 2 down, you still get 2. So this is v sub 1 plus v sub 2 plus 2. Now I'm going to replace v sub 2 with 2v sub 1 plus 2. So this is v sub 1 plus 2v sub 1 plus 2 plus 2. This simplifies to v sub 3 equals 3v sub 1 plus 4. Now let's evaluate v sub 4. According to the recursive definition, this is v sub the floor of 4 over 2 plus v sub the floor of 4 plus 1 over 2 plus 2, which is v sub 2 plus v sub 2 plus 2, which v sub 2 was 2 times v sub 1 plus 2, so we can replace these v sub 2's with that expression. And then we can combine like terms. This simplifies to 4v sub 1 plus 6. Now I'm noticing a pattern. I'm noticing that whatever the value of the index variable is happens to be the coefficient in front of the v sub 1. So when the index value is 3, the coefficient in front of the v sub 1 is 3. If the index value is 4, the coefficient in front of the v sub 1 is 4. I'm also noticing that the constant is incrementing by 2. So this is 2 times 1, this is 2 times 2, and this is 2 times 3. It's going to be 2 times whatever the value of the index variable is minus 1. So my guess, and this is just a guess for now, is that v sub 5 is going to equal 5 times v sub 1 plus 8. But just to make sure, let's see if this is true. V sub 5, according to the recursive formula, is v sub the floor of 5 halves plus v sub the floor of 6 halves plus 2, which is just v sub 2 plus v sub 3 plus 2. Now v sub 2 was 2 v sub 1 plus 2, and v sub 3 was 3 times v sub 1 plus 4, and then plus 2. If we simplify this, we get 5 v sub 1 and then plus 8, which is exactly what I predicted. Now, in this case, I think we should generalize before we substitute v sub 1 here. In general, v sub n is equal to n times v sub 1 plus 2 times n minus 1. And we can substitute v sub 1 equals 1 into this expression to get n plus 2 times n minus 1, which simplifies to 3n minus 2. So v sub n is just 3n minus 2. Now, that's actually quite a surprisingly simple explicit formula for part A, but that's the solution to part A. Now, let's prove that this works using strong mathematical induction. So this is going to be our P of n. The base case is going to correspond to when n equals 1. P of 1 is just the statement that v sub 1 equals 3 times 1 minus 2. I'll put a question mark, though, just to avoid asserting this conclusion. But v sub 1 is given to us. V sub 1 is 1. And we can evaluate the right-hand side of this p of 1 to get 3 minus 2, which is also 1. And so p of 1 is true because v sub 1 equals 3 times 1 minus 2. Now let's move on to the inductive step. Now, since we're doing strong mathematical induction, we might need more base cases. I'm not sure yet how many base cases we need. We might need 1, we might need 2. We might need only just 1, though. But it really depends on how we evaluate this inductive step. So I'm going to leave some room in the base case just in case we need more base cases. In strong mathematical induction, the inductive step looks a little bit different in the beginning. We're going to say let k be an arbitrary fixed integer with k greater than or equal to 1. Keep in mind, remember that this number has to be the largest base case that we proved in the base case section of this proof, which in this case is just 1 for now, but we might need more later on. And then we assume that for all I in the range 1 less than or equal to I less than or equal to k, this 1 corresponds to the smallest base case that we proved, which we already know has to be 1. And we're assuming that p of I is true, meaning that we're assuming that p of 1 is true, and p of 2 is true, and p of 3 is true, and p of 4 is true, all the way up to p of k. The inductive hypothesis is just that v sub I equals 3i minus 2 for all I in this range from 1 to k. We want to show that v sub k plus 1 equals 3 times k plus 1 minus 2, which is just 3k plus 1. To prove this, we're going to start with the left-hand side, which is v sub k plus 1. Now, k is greater than or equal to 1, which means k plus 1 is greater than or equal to 2. The reason that matters is because if we go back up to our recursive definition here, we can only apply the recursive definition for integers greater than or equal to 2. But luckily, since k is greater than or equal to 1, that means k plus 1 is greater than or equal to 2, which means we can apply the recursive definition to v sub k plus 1. So v sub k plus 1 equals v sub the floor of k plus 1 over 2 plus v sub the floor of k plus 2 over 2 plus 2. Now k is an integer, but k plus 1 over 2 will either round down to k over 2, or it just won't round down at all. This will just be k plus 1 over 2. Maybe it's already an integer. But that depends on whether or not k is even or odd, which means this is where we need to break our inductive step into cases. So case 1 is going to be k is odd, and case 2 is going to be k is even. If k is odd, then that means k plus 1 is an even integer. And if you divide k plus 1 by 2, since k plus 1 is an even integer, then k plus 1 over 2 is already an integer. So we could say that v sub k plus 1 equals v sub k plus 1 over 2, and we don't need to round down here. But since k is odd, then k plus 2 is also going to be odd. And if you divide that by 2, you're going to have to round down. And this is going to round down specifically to k plus 1 over 2, and then plus 2. Now I want to apply the inductive hypothesis. We know things about v sub I when I is in between 1 and k. But we need to make sure that k plus 1 over 2 is in this correct range before we apply the inductive hypothesis here. So I'm going to make a note under here that since k is greater than or equal to 1, we can add 1 to both sides to get k plus 1 is greater than or equal to 2. And if we divide both sides by 2, we get k plus 1 over 2 is greater than or equal to 1. Moreover, since k is greater than or equal to 1, that means k plus 1 over 2 is less than or equal to k. If you cut something in half, you're usually going to make it smaller. And that's particularly true here when k is greater than or equal to 1. Keep in mind, though, that we can work backwards from this conclusion to start from a tautology instead. This would say that k over 2 plus 1/2 is less than or equal to k, and we could subtract k over 2 on both sides to get 1/2 is less than or equal to k over 2, and then we can also multiply both sides by 2 to get 1 is less than or equal to k, which we know this to be true based on the assumption. So the logic works backwards here. If we start by saying k is greater than or equal to 1, then we could divide both sides by 2, and then we can add k over 2 to both sides, and then combine the fractions on the left-hand side to get k plus 1 over 2 is less than or equal to k. This is all to show that k plus 1 over 2 is in the range from 1 to k, which is perfect, because this means that p of k plus 1 over 2 is true. And so this is where we apply the inductive hypothesis. The inductive hypothesis tells us that p of k plus 1 over 2 means that v sub k plus 1 over 2 is just 3 times the value of the index minus 2. So this is just 3 times k plus 1 over 2 minus 2. And that's by the inductive hypothesis. We need to tell the reader that we're using the inductive hypothesis here. Now that we have an expression for v sub k plus 1 over 2, we can substitute in this green expression here to get that v sub k plus 1 equals 3 times k plus 1 over 2 minus 2 plus 3 times k plus 1 over 2 minus 2 plus 2. These 2's cancel, and this simplifies to 3 halves k plus 3 halves, and then I'll leave this minus 2 to the end, and then another plus 3 halves k, and then plus another 3 halves, and minus 2, which simplifies to 3k. 3 halves plus 3 halves is 3, minus 2 is 1, plus 1. So v sub k plus 1 equals 3k plus 1, which is what we wanted to show. What we wanted to show is that v sub k plus 1 equals 3k plus 1. Perfect. So we've proven that this is true for case 1. Now we need to move on to case 2 when k is even. So far, by the way, we haven't needed an additional base case yet. There's nothing in this inductive step that requires us to prove multiple base cases yet, but we'll see for case 2. Now, since k is even, we can say that k plus 1 over 2 is going to round down to k over 2. So v sub k plus 1 equals v sub k over 2, and then since k is even, k plus 2 is also even, and if you divide an even number by 2, then you're going to get an integer. And if you round down an integer, nothing changes. So this is going to simplify to v sub k plus 2 over 2. And then we have an extra plus 2 here. So that's how we drop the floor functions when k is even. Now, k is even and k is greater than or equal to 1, which means that k has to be greater than or equal to 2, since k is even. The smallest integer that's even, that's greater than or equal to 1, is 2. But if we divide both sides of this inequality, this means then that k over 2 is greater than or equal to 1. And we could say the same thing about the other fraction. K plus 2 over 2 is also greater than or equal to 1 because k over 2 is greater than or equal to 1. If you make the numerator bigger, then you're going to make the overall fraction bigger. Also, we should mention that k over 2 is less than or equal to k. Since k is positive, if you cut k in half, you're going to get a smaller number. We also need to know that k plus 2 over 2 is less than or equal to k so that we can use the inductive hypothesis. Now we want to show that k plus 2 over 2 is less than or equal to k. Now we can work backwards from this conclusion to get that k plus 2 would have to be less than or equal to 2k, and we can subtract k on both sides to get 2 is less than or equal to k. So we can work backwards here, starting with the fact that k is greater than or equal to 2. We can add k to both sides, and then divide both sides by 2. So what do all these inequalities mean? This means that we've shown that k over 2 is in this very important range from 1 to k. We've also shown that k plus 2 over 2 is also in this very important range from 1 to k. By the inductive hypothesis, this means that p of k over 2 is true. And also p of k plus 2 over 2 is true. Now keep in mind the inductive hypothesis says that v sub I equals 3i minus 2, And so in particular, what we've shown is that v sub k over 2 is 3 times k over 2 minus 2, and also v sub k plus 2 over 2 equals 3 times k plus 2 over 2 minus 2. So now let's go back to this expression and plug in what we have for v sub k over 2 and v sub k plus 2 over 2. So this means that v sub k plus 1 equals 3 times k over 2 minus 2 plus 3 times k plus 2 over 2 minus 2. And then we still have this plus 2 here. These 2's cancel, and we can distribute the 3 to get 3 halves k minus 2 plus 3 halves k, and then 2 over 2 is just 1, and if you distribute the 3 to that 1, you get 3, so this is plus 3. 3 halves plus 3 halves is just 3, so this is 3k, and then minus 2 plus 3 is plus 1, and we get 3k plus 1 again. So if you notice, in case 1 and case 2, we get 3k plus 1. And notice nowhere here did we require an additional base case, which is very rare, by the way, with mathematical induction. But this means then that p of k plus 1 is true, which by mathematical induction means that p of n is true for all integers n greater than or equal to 1. Thanks, everyone, and I'll see you in the next video.